Well, a warm welcome to anyone joining. Thank you for being here. Go ahead and get yourself ready with a notebook. You can grab a pencil or a pen. Whatever you choose to write with is fine. This is some physics from the void. Physics coming at you out of nowhere. Didn't think the intro through on that one, but yeah, who knew? I know some physics as well. And I have some physics students that I work with. If you're interested in physics, or if you're taking Physics 1, this would be a video dedicated to two-dimensional kinematics motion. It's a bit of a challenge problem. It's not unattainable for someone who's just a math student, but there are a couple of concepts here that you would learn in physics which you might not know just from studying mathematics. But nobody is excluded. You're all welcome to be here, and I appreciate that you're here. Here we have what I consider to be a star problem, because if you haven't yet broken into the realm of two-dimensional motion thoroughly, it could be a little tricky. It's a multiple choice question, so you could get the answer correct even if you have no clue what to do here. You can guess with 20% likeliness that you will have the correct answer. Go ahead and take the time, about maybe 7 minutes, 8 minutes or so, to try to figure this problem out by yourself first. You can pause the video, see if you can figure it out, and then if you're ready, you can unpause the video and see how I do it here. Now, I think this is one of the most structured ways to solve these two-dimensional motion types of problems. So here, let's read the problem. We have a projectile is fired horizontally. That is important. It's going to tell us something about the starting velocities. Projectile is fired horizontally from a height of 20 meters. So from a height of 20 meters, they're giving you some information above the ground with an initial velocity, there we go, of 7 meters per second. The question is, how far does the projectile travel horizontally before it reaches the ground? Okay, so the best thing to do with this is to draw a diagram. So we're going to start off by drawing a bit of a diagram. We're going to imagine some random 20-meter cliff and an object that is shot straight forward, right? Directly forward. Something like that. And we're told that its initial velocity is 7 meters per second, but I'm actually going to label it as v sub x because this velocity is only applied in the horizontal direction. Yes. And what that means is that there's technically zero velocity in the vertical direction to start. Our question is, how far forward? If you were to throw an object forward, what would you imagine? It's going to go forward and then it's going to fall, right? We want to try to answer the question of how far in front of where it was thrown does this object land. So the best way to get started with this is to make an information chart representing the horizontal on one column and representing the vertical on another column. The quantities that we want to deal with in kinematics are time, acceleration, v initial, v final, and distance, which we might call delta x, or if we're talking about vertical distance, we would call delta y. Now, the question does not ask about the vertical distance at all, so we don't really need to worry about the vertical distance. Let's write down some given information. We do know what the vertical distance is, because if it's going to fall down 20 meters, then our delta y, or our change in vertical position from start to finish, is 20 meters in the negative direction. Our delta x, that's what we're after. Let's use some of the initial information, which is that the initial velocity in the x direction is 7 meters per second. Meanwhile, the initial velocity in the y direction is 0, because when we start this problem, the projectile is launched horizontally, straight forward. It's not launched up or down at any angle. It's not going up or down with any speed at all. Now, some important feature of kinematics is acceleration. And you need to remember this for kinematics problems in 2 dimensions. Whenever we have an object being thrown into the air, the acceleration due to gravity is 0 in the horizontal direction. Gravity does not push things horizontally. Hopefully you know that by the fact that you're either standing or sitting or somehow connected to whatever's beneath you, thanks to gravity. Now, on the other hand, the acceleration due to gravity in the y direction is negative 9.8 meters per second squared. And the glue, what do I mean by the glue? The glue, which connects these 2 dimensions of motion, both the horizontal and the vertical, is time. So time will be the same across both dimensions, which makes sense. Even though this object is moving horizontally at first, it starts moving horizontally and vertically as it falls, and then it finally hits the ground. When that happens, the same amount of time has passed, whether you're thinking about this in the vertical or in the horizontal. The one quantity that is the same between the vertical and the horizontal is time. Because time keeps track of the entire situation. It doesn't just focus on one dimension of motion, right? So knowing this, what is our strategy? Our strategy for problems like this, where an object's being thrown into the air somehow, is to find the time using the vertical info. And that's because how long this object stays in the air only depends on the vertical information. It depends on how far does it have to drop and how strong is gravity. Those 2 things alone are going to dictate. And also if there was an initial speed. So if I threw the object upwards in the air, just like if you throw a ball up in the air, it's going to stay in the air longer than if I just dropped it or threw it straight forward. So some of the vertical information is the important information. And we're going to use the following formula, which says delta y equals 1/2 at squared plus v, sometimes they put a v0, sometimes they put a vi. You're going to see me go back and forth. I'm going to put vi at this time to stay consistent with what I did above. All right, there we have it. So what's interesting about this, and if we wanted to, we could turn this into a function for you math heads, for you math kids. We could call this y of t, which means the position after a certain amount of time. But if we do that, we would have to include our initial y value as well, which happens to be 20 meters in this case. I'm going to turn it back into the physics version, which subtracts the initial y position on the other side and therefore results in delta y. And I'm going to show you that in the vertical direction, whenever something is thrown horizontally, we conveniently are able to eliminate the second term because the object has a starting velocity of 0 in the vertical direction. Now you might say, what are you talking about, the velocity is 0? It's not 0, it's 7 meters per second. Didn't we just read that? It is 7 meters per second, but it's fired horizontally, which means none of that 7 meters per second is at all contributing to the vertical velocity. So conveniently, this entire term just drops out because 0 initial velocity times the time will always be 0. So let's write it as this. Negative 20 equals negative 4.9. I'm going to drop the units and just calculate with numbers. That's kind of sloppy. And if it's for AP Physics or anything like that, I would be a lot more disciplined and write the units for 2 reasons. 1, because it's accurate, and 2, because it kind of helps you keep track of your quantities. If you end up with a certain quantity in the wrong units, that means you either wrote something incorrectly as a typo or you actually did something wrong. So it kind of helps you keep track here. Since there's not a lot of crazy units going on, it's clear that we're just solving for time. I'm not going to worry about that too much. We're going to divide both sides by 4.9. And we're going to get approximately, it's almost 4 because 4.9 is almost 5. Let's call it like 4.1 or something. You could use a calculator if you want to get a very specific answer, but we're going to get close enough from this that we'll be able to figure out the right choice, the answer choice with multiple choice. So if we take a square root of both sides, we get the amount of time it takes for the object to drop 20 meters. And this is going to be approximately not even 2.1. It's going to be like 2.02 probably, like something really small. So let's just call it 2 for the sake of easy maths. This tells us how long the object is in the air. It hits the ground 2 seconds later, and now we get to use the glue. Here's how we use the glue. Since it takes 2 seconds to fall, I get to go on the other side, the horizontal side of things, and I get to plug that 2 seconds in. Then I can ask myself, how far did it go? Well, we're going to use a very similar equation. Delta x equals 1/2 at squared plus the initial velocity times t. The difference is that the initial velocity here does not drop out because we have an initial velocity of 7 and we have the time of 2. What is going to drop out, funny enough, is this first term. So when we look at the horizontal side of things, the first term drops out. There is 0, the first term drops out. Let me move this entire box here. First term drops out because the acceleration in the horizontal direction is 0. Right? Acceleration is 0 in the horizontal. Even though we threw the object, it is not being accelerated after it's released. That's the idea. We definitely had to give it acceleration to throw it, like before we let go of the object. But once it's let go of, once it's launched, it is only under the influence of gravity, which means the a in the x direction is 0. So really our delta x just equals 0 plus 7 times 2, or 14 meters. That is how far it goes. It's very interesting to think about this concept that if we neglect wind resistance and air resistance, this is not the most realistic situation, but if we neglect those things, then the object should be moving the same speed horizontally the whole time. The only thing that changes is it gets pulled down. In other words, if gravity weren't stopping it by pulling it down to the ground, it would just continue going straight. I mean, even a bullet gets pulled down to the ground. So even a bullet technically speeds up as it's falling because it goes roughly the same speed forward, but it increases its speed going downward as it drops towards the ground. Okay, so that means we're looking at option B. That is the correct answer. I hope the breakdown of this in a vertical and horizontal components was really helpful for you. This is going to be a key diagram to use, or a key tool to use whenever you're answering questions about two-dimensional motion, particularly useful when we're talking about projectiles. In fact, this is called projectile motion in kinematics. Okay, I think that's enough blab out of me. I'll see you guys next time.